All right, welcome back to now section 2 of the ecology notes. So we're going to look then at energy relationships in the biosphere. So how does energy affect the biosphere that we just talked about, the atmosphere, the climate, the weather? How is that affected? So climate on Earth is got many interacting factors that are going to be responsible for creating it, but none is more important than insulation. Insolation is the name given to the energy coming in from the sun. All of the energy that initially gets onto the earth comes from the sun, and in the form of solar energy, also known as radiant energy. You've seen this. I've showed you a electromagnetic spectrum when we were doing plants. I was showing you the electromagnetic spectrum, so all the different kinds of light, the energy that arrive from the sun, from the gamma rays to the X-rays to the UV, and then the visible, infrared, and the radio waves. But most of the solar energy that enters the Earth's atmosphere is converted to thermal energy, heat. Some of it, as we saw in biology, is transformed into chemical energy. Example, photosynthesis, right? But most of it is actually going to be converted into thermal energy. So thermal energy, or heat, is the amount of energy that is found in the molecules or in the atoms of a substance. It is the kinetic energy, the energy of motion of those substances. And thermal energy, or heat, as we know, is generally greatest near the equator. So here we're going to have sort of warmer temperatures, and it is least near the poles. And so here is going to be much colder. So why is that? And again, that has to do with insolation. Insolation is the amount of solar energy received by a region of the Earth's surface. And there are several aspects that are going to affect insolation. We're going to look at latitudes being the first one. So latitude, these are the lines that run parallel to the equator. And you can see here, these lines are parallel to the equator. And so equator is 0. degrees, so that's the equator, that's the middle, and that's where we do not have an angle at all to the sunlight that comes in. And then if we look at 90 degrees north, that's the North Pole. And if we go 90 degrees south, That's the South Pole. And so all of the other latitudes are going to have different degrees. So there used to be a show on CBC called North of 60. And so it was a show about a population or a group of people that lived in this area right here, north of the 60th parallel, okay? And so that's what those lines are. Now, the shape of the Earth, because the Earth is not flat, is rounded, it's a globe, it's going to affect the insolation of regions that are at different latitudes, okay? And a lot of the incoming radiation is not going to be perpendicular to the surface because we're not dealing with a square that the light is just going to hit straight. It doesn't matter where on the square you are. We are dealing with the globe. And so what that's going to happen is it's going to hit at an angle. Blue. And this angle is called the angle of incidence. So this is the angle between a sun ray hitting the Earth's surface and the line perpendicular to that surface. Okay. Or the amount of deviation. How much does the angle deviate from the perpendicular? Okay. The greater the angle of incidence equals less insolation. So for example, here you can see that at the equator, we have the rays are hitting as a rectangle, okay? So we get the surface area that is covered by the rays is this. So let's say that we always are starting with the same amount of sunshine. It's the amount of sunshine that arrives is not different, okay? So this is how much of it is going to be hitting that surface. But then what we start to do is we start to see this, okay? And so what we're doing is we're taking that same amount of energy, but we have to spread it just a little bit further up. And then same thing here, as you can see, we're taking that same amount of energy and we're spreading it just a little bit more up. And then when we get to the higher latitudes, you can see here just how much more we have to spread that same energy over a larger area, right? So the surface area that is covered by the same amount of sunlight is more, and therefore it's more sprayed out. So at the equator, the angle of incidence is 0. And as you move towards the pole, the angle gets greater and greater. At larger angles of incidence, the same amount of solar radiation, the same amount of solar energy is spread out over a larger area, okay, over a greater surface. I'm just actually gonna try and write all of that in there. Whoops. Is spread out over a larger surface. So less solar energy per kilometer squared, okay? So I'm hoping that that makes sense. The number of daylight hours is a second factor that is going to be affecting the amount of insolation, how much sunshine actually that area receives, okay? So we saw that the angle of inclination makes it so that some of them receive less and some of them receive more. The number of daylight hours will have the same effect, right? So the Earth is not facing the sun perpendicularly. So the Earth is not like this. We know that the Earth is at an angle of 23.5 degrees, okay? And they actually say that it was a collision with a very large celestial object that gave us the moon eventually, that tilted the Earth, that shifted the Earth into this particular angle. Okay, so again, that series will also, that I mentioned in the first video, will also tell you all about that. Okay, so the angle of inclination, this is the degree by which the Earth's poles are tilted from the perpendicular. Of the plane of its orbit. Okay, so facing the sun. And the angle is always 23.5 degrees towards the sun. Okay, so if you hold the Earth in this shape right here, as it's going around the sun, right? So as it's spinning around the sun, it'll always be like this. So it doesn't matter. It'll always be facing towards the sun, okay? The angle of inclination is going to cause variation in the number of hours of daylight at different latitudes, okay? And because at certain times, as you can see here, the Earth is going to be tilted towards the sun in the northern hemisphere, and then it's going to be tilted away from the sun in the southern hemisphere. And as it's spinning around itself as well, you're going to have sort of the daylight hours, and then you're going to have the seasons as well. So the seasons that as it's going around the sun, and the day is obviously as it's spinning around its axis. Now the time of year, also known as the seasons, we know that the Earth orbits around the sun once every year. It actually is once every 364.25 days. Okay, so it's not 365 days, it's 364.25. And that's why every 4 years we get a leap year, okay? Because of that extra day that we get in February is because of that quarter, okay? So the first day of summer, which is in the northern hemisphere where we're at, is going to be June 21st. The angle of inclination will cause the North Pole to be tilted towards the sun, okay? So when we look at that very first day of summer, this is where we're at. So the northern hemisphere is tilted towards the sun and the southern hemisphere is not. So when it's summer here, it's going to be winter in the southern hemisphere. Okay, so that's why, you know, when you get to summer, this is when the southern hemisphere in December, they're having their summer and we're having our winter. Okay, and this results in warmer weather in the summer because we have more insolation. And colder weather in the winter because of less insolation. Okay, and I'm talking about insolation, not insulation like the one that you have in your house, the padding. Okay, insolation means how much sunshine. And so a couple of terms that we need to make sure that we know or review. The solstice. So the solstice is one of 2 points. So there are 2 solstices. In the Earth's orbit. Around the sun, not around itself. At which the poles are tilted towards the sun. Or away from the sun, okay? I should say towards, away from sun. And so June 21st, the longest day, okay, in the northern hemisphere, shortest in the southern hemisphere. So this is the summer solstice, summer solstice. And then there is the winter solstice, which is December 21st, and that's going to be the shortest day, okay? Whereas the equinox, I want you to think of equal. This is one of 2 points in the Earth's orbit where the number of daylight hours is equal. Equal number of daylight as we have nighttime. So the sun rays here are going to hit directly at the equator, and the 2 equinoxes are the spring and the fall equinox, right? So this is spring and this is fall equinox, okay? So the result is that there is more variation from season to season in daylight hours, in insolation, and therefore the temperature is going to also fluctuate as you move towards the poles and towards the equator. So the result is, I'm just going to write it in a different color here. Variation from season to season and number of daylight hours and therefore temperature at the poles and at the equator. Now, because the equator is constantly getting sunlight directly, what you're going to see, you're not going to see a fluctuation in temperature at as much as you see as you move away from the equator, okay? Now, another factor that is going to affect climate, it's not just the amount of sunshine that reaches the Earth, but it's also the amount of sunshine that is allowed to enter the Earth, right? Because a lot of sunshine, a lot of sunlight, a lot of energy from the sun is going to be absorbed, and some of them is going to be reflected by the biosphere, okay? So as soon as the radiation from the sun reaches the Earth's atmosphere, there's going to be a number of things that are going to either reflect it or absorbed by particles of matter. So for example, the ozone is going to absorb most of the ultraviolet radiation from the sun. In fact, ozone itself is O3 as a formula. And what starts to happen is you have a whole bunch of oxygen, and when UV light hit it, it splits it into O and O, and then they can join the O2 to make the O3. Okay, so that's what that UV ray is used for, is to make more ozone. Okay, so we need ozone to split those O2 molecules so that we can make O3. Okay. Carbon dioxide, water, and methane. These are known as greenhouse gases, carbon dioxide, methane, water vapor. So what they do is they absorb infrared heat, radiation, And so they're known as greenhouse gases because they keep the earth warm, just like a greenhouse allows heat from the sun to come in but not to exit. These carbon dioxide, water, and methane allow heat to come into our planet, but they don't allow it to escape. And so it keeps the temperature at a range that is livable, that is allowing life to be harbored. Gases in the upper atmosphere, we talked about those gases in the very upper atmosphere. They are the ones that are going to absorb the X and gamma rays, those harmful rays from the sun that we don't want here. And so you can kind of see what happens here. So 20% of that energy from the sun gets scattered and reflected back out into space. 6% of it, again, gets scattered, reflected back into space by the atmosphere. 19% gets absorbed, and it drives things like our weather system. And then of the light that actually does come in, of the energy of the sun that does come in, 51% of it is absorbed by the earth. And the earth itself also has reflectivity, and so 4% of that light gets reflected. Okay, so you can see that we have a lot of rays of sunshine, infrared for the most part, that come in, whereas things like visible light, radio waves, they make it to your surface with very little absorption, and so we can see with that, and we can use those radio waves as well. Okay, atmospheric dust and clouds, they can shade the surface of the earth from incoming solar radiation. We see here on a cloudy day how the clouds are going to be preventing that sunshine from coming in, and they can also absorb some radiation reflected from the surface of the earth. So that sunshine is coming in, it's going to be bouncing back, and then the clouds, that cloud cover, can absorb that sunshine, and so it can make the area much cooler. We call that the albedo effect. The albedo effect is the percent of solar radiation that a surface can reflect. So the higher the albedo, the more reflective a surface is. So lighter colors will reflect a high percentage and therefore have a high albedo. So a mirror, for example, would have a very high albedo. Water cover, like a lake, snow-covered ground will have high albedo, will reflect. Whereas darker colors, they tend to absorb or reflect a lower percentage. And therefore have a low albedo. So dirt cover is going to, the more dirt you have, the more rock and soil you have, the more it will absorb that heat, the hotter it will become, okay? Cloud cover, atmospheric dust, as we saw before, even forest cover, because, what's it called? Plants will have some transpiration, some water, some droplets on their leaves, so they will reflect, okay? These kinds of things will decrease the amount of heat that is absorbed. And therefore, forests are going to be warmer without trees. So deforestation can cause temperature increases, right? Whereas clouds increase it. So it is cooler with clouds. Okay. Deforestation, not a good thing. Our planet is going to get warmer because it's going to absorb more energy from the sun. Clouds will increase the amount of albedo, the amount of reflectivity, and therefore it's going to be cooler when we have clouds around. Okay, so the greenhouse effect is what this is talking about. The greenhouse effect, this is the, I'm going to use purple here because it's an important definition. The absorption of thermal energy that is reflected off the surface of the Earth by atmospheric gases so as also known as greenhouse gases. As the energy from the sun comes in, it bounces off the surface of the Earth, be it off of water bodies or snow or forest, and this blanket of greenhouse gases that we find in our atmosphere prevents that energy, that thermal energy, from leaving. It gets absorbed. It stays near the surface of the planet. So we need greenhouse gases to keep the temperature of the planet warm enough so that we can live on it. But the problem is not the fact that we have a greenhouse effect, is the fact that we are exacerbating it. We're making it worse. Okay, so if you think of, again, these greenhouse gases as a blanket that is found in our atmosphere that allows the sun rays to come in, but it doesn't allow them to get out. Right? It doesn't allow them. Some of them will escape, but not all of them. Some of them will be kept in. What happens if I put another blanket and then another blanket and then another blanket? Now, none of those rays are going to be allowed to escape. They're all going to stay in here. And so the planet's surface, the heat, the energy that we trap inside the surface of the planet increases. Because of that, we're going to have more evaporation, we're going to have melting of the ice caps, we're going to have unstable weather conditions, okay, that are going to come to life, right? So these greenhouse gases, we said before, water vapor, methane, nitrous oxide, and the biggest contributor, carbon dioxide. Now, the reason why it is the heaviest contributor is because of human activity. What we've seen since the Industrial Revolution is a drastic increase in the amount of CO2 that is found in the atmosphere, in the amount of CO2 that is part of that greenhouse effect. And so because of the contribution from human activity, CO2 levels have increased. We are increasing the number of blankets that we are putting on the surface of the planet. Okay, so albedo, cloud and dust cover, the greenhouse effect, they all interact with the natural insulation from the sun to give the planet a particular net radiation budget. A net radiation budget is the difference. Again, I think I'm going to go purple here. The difference between the amount of incoming radiation, so how much heat is absorbed, and the outgoing radiation. This is the heat reflected out for the planet. Okay, so if you think about a budget in your house, is how much money are we bringing in and how much money are we spending? So the net radiation budget is the difference between how much heat is coming in and how much heat is leaving. Now, the closer to the poles you are in latitude, what you're going to see is the more radiation is reflected rather than absorbed. So you have a deficit in the amount of heat, right? If more of it leaves than comes in, you have a deficit, and therefore you're going to be colder. Whereas near the equator, you have more that is being absorbed than reflected, and therefore you're going to have a surplus. All of it is going to even out. And if the balance were to change, then the average global temperatures would either increase or decrease. And that's what we call global warming, right? So that's what they mean by global warming. And so when some people say, oh, it's so cold in Edmonton. How come, people talk about global warming? There's no such thing. It's not about one particular area. You're talking about a balance between what comes in and what comes out at the poles and the equators. The amount that is coming in at the equator is going to be the same. But if now the amount that is coming in at the poles increases, you don't have that balance between in and out. And so global warming, we have the same amount of energy coming in, but not as much as leaving. And therefore, you're going to have an increase in global temperatures. And that's going to lead to global climate change. And we're going to see why that is in our next section, because we're going to see how thermal energy is going to affect things like energy transfer between different parts of the earth. Okay, so I hope that section is pretty clear. We're going to continue, like I said, next time with thermal energy transfer in the atmosphere, and then we'll move on to water and how water plays a role in all that. We'll see you next time.